Hi, I am Jimmy Leppink, psychologist and statistician, and in this video I explain the Bayesian binomial form of the percentage of all non-overlapping data, or PANDB, as a non-parametric statistic for all types of variables and distributions and for large and small samples. Key in this statistic is the concept of non-overlap, which can be applied consistently to both qualitative and quantitative data and can provide an estimator of effect size in qualitative, quantitative, and mixed methods research. This principle of non-overlap in the form of PAND is not new, as we will see in a few minutes. It is a statistic that was proposed in a scientific article about 16 years ago. What is new about PANDB is that PAND is conceptualized as a binomial process in which every observation of non-overlap is treated as a success and every observation of overlap is treated as a failure. In addition, a prior distribution is added, which, in the absence of any prior knowledge, is one of a single success and a single failure. As is common in Bayesian analysis, the posterior resulting from combining the prior and data at one occasion can serve as a prior for future data collection occasions. Simultaneously, in the case of small samples and no prior knowledge, this default prior provides a penalty for extreme outcomes in small samples. In some areas, there are claims that statistics cannot be used for qualitative data, yet this statement flies in the face of decades of research on qualitative measurement. Although there are different ways to categorize qualitative and quantitative variables, I usually categorize them as follows: dichotomous, multi-category nominal, multi-category ordinal, and quantitative. Key difference between multi-category nominal and multi-category ordinal variables is that in the case of the latter, there is a natural order in the categories, such as poor performance, satisfactory performance, and strong performance. Although the difference between poor, satisfactory, and strong performance may not always be the same, it is clear that strong is always better than satisfactory, and satisfactory is always better than poor performance. In essence, with the exception of quantitative or scale variables, the data types depicted here are qualitative data types. Yet, all four data types, including quantitative, can be conceptualized in terms of overlap or non-overlap, as we will see next. As I already mentioned at the start of this video, PAND is a statistic that was proposed about 16 years ago by Richard Parker and colleagues, although it existed only as a point estimate or observed percentage without any sampling distribution or confidence interval around it. A few years ago, I reconceptualized this statistic as a binomial process in which every observation of non-overlap is treated as a success and every observation of overlap is treated as a failure on this dimension of non-overlap. And I added the prior distribution for reasons mentioned earlier, and in the book in which I introduced this PANDB statistic, which got published with Springer in 2020, I also propose a variant of PANDB to deal with multi-level structures in data. When samples are very small, the default prior, in my view, provides an appropriate penalty for extreme events in small samples, such as 100% non-overlap in a sample of 10 or fewer observations, and therefore results in a point estimate for PANDB, which is slightly closer to 50%, or expressed on a scale from 0 to 1, closer to 0.5, than the point estimate for PAND. However, with increasing sample size, this difference decreases and gradually approaches 0. Roughly speaking, PAND and PANDB can be converted into correlations more or less by doubling the PAND or PANDB estimate and subtract 1 from that product. As a consequence, a PAND or PANDB estimate of 0.5 corresponds with a correlation of 0. PAND or PANDB estimates below 0.5 correspond with negative correlations, and PAND or PANDB estimates above 0.5 with positive correlations. Now, if you are interested in seeing an example of PANDB for each of the 4 data types distinguished earlier, here I provide a link to an open access article for each data type. And I will also briefly discuss 3 examples in the remainder of this video. In this first example, we deal with a dichotomous outcome variable that we want to compare between 2 groups called group 1 and group 2. We have a sample size of 18, and 3 of these 18 cases contribute to a deviation from 100% non-overlap. This is the key question in PAND. How many observations would we need to remove or to swap from one group to another in order to create a 100% non-overlap or perfect non-overlap, which would be a correlation of 1 or -1 depending on how we code the groups. This translates into a binomial distribution of 15 successes and 3 failures, which in combination with the default prior results in a posterior distribution of 16 successes and 4 failures, which is a distribution with a median of 0.81 and a 95% credible interval, which is the Bayesian counterpart of the confidence interval. So a 95% credible interval here from 0.604 to 0.939. These numbers, by the way, can easily be computed in open source programs such as R, JASP, and Jamovi. The 95% credible interval exceeds 0.5, which indicates that a PANDB of 0.5 or a correlation of 0 can probably be rejected. In addition, it exceeds 0.6, indicating that even PANDB values below 0.6 or correlations below 0.2 can be rejected. In larger samples, this procedure can also have sufficient power to detect cases or situations of practical equivalence, for instance, PANDB intervals between 0.4 and 0.6. Note, however, that this is not a plea to replace other statistics for this kind of two-way tables with PANDB, by no means. Simply, the aim of this example is to introduce PANDB with an example of this kind of table and see similarities later on with different kinds of situations, situations that we will see in the next couple of minutes. In this second example, we deal with 2 groups that are compared on a quantitative outcome variable that has distributional features which are difficult to account for with a traditional t-test. We have a sample size of 14 observations, of which 3 observations contribute to a deviation from 100% non-overlap, and these are the numbers in red. So this creates the outcomes for PANDB below this table. Important to note, here we have the PANDB above 0.5 because we code in favor of the experimental group, meaning that better scores in the experimental group in this case means higher PANDB values. Suppose that these were the data, but that the data which are now for the experimental group were actually the control group data, and the control group data that we see now were the data for the experimental group. In that case, we would not have a PANDB point estimate of 0.76, but of about 0.24. No, and the 95% credible interval wouldn't range from 0.52 to 0.92, but from about 0.08 to about 0.48. So just to give an example here as well of PANDB values which can go below 0.5 and would in that case indicate negative, in this case a negative treatment effect or negative correlation. Although this example, that's another important point, this example and the previous one focus on two-group comparisons, PANDB can be applied to situations where more than two groups are concerned, and even where the relation between two quantitative variables is of interest. And again, note that that the idea of this example is not to hold a plea for replacing other statistics, parametric or non-parametric ones, with PANDB, but again to understand the transversal potential of PANDB, which is to say its applicability across variable types. Finally, in this third example, we apply PANDB to a single case design in which a single participant in 14 clinical cases chooses one of three methods for surgery, A, B, or C. And we want to know if after a training program there is a change in method preference compared to before the training program. In this case, only two observations create a deviation from 100% non-overlap, and hence the outcomes for PANDB are as displayed below the time series. And in line with the previous two examples, please note that this is not a call to from now on use PANDB and forget about other statistics for this kind of data. On the contrary, PANDB provides a reasonable statistical solution in time series of very limited sample size, which simply lack the information to appropriately account for the kind of serial correlation that is common in time series. While in the case of a time series with a quantitative outcome variable, certain linear model solutions may more appropriately account for serial correlation and trends in the data. Time series of this size with categorical outcome variables simply tend to lack the information that is needed to appropriately account for any kind of serial correlation. And in that case, having a statistical solution like PANDB is better than not having a statistical solution. Especially if in this case the statistical solution is one that can also be used for other data types and has a transversal character, can facilitate qualitative, quantitative and mixed methods analysis. As explained in the examples in this video as well as in the articles referred to in which PANDB is applied to different data types, PANDB constitutes a non-parametric statistic for all types of variables and distributions and for large and small samples. However, where the sample size and data features allow for the use of statistics that are more appropriate for each data type, PANDB is at best a complement to allow for comparisons between data types, but should not be used as a standalone statistic because it comes at a loss of information compared to alternatives. For example, as I already briefly mentioned, in time series with quantitative outcome variables, unless there are extreme cases or other types of obvious deviations from linear trends, first order, autoregressive or moving average linear model solutions may appropriately account for serial correlation in the data, even for relatively small samples, and as well as for trends in specific phases of the time series, such as before versus after the training program. And this kind of account cannot be provided by a non-parametric statistic like PAND or PANDB. Like any statistics, PAND and PANDB have their limitations and provide no solution for all small sample size or strange distribution issues. That said, what PANDB with its credible interval can provide is an estimation and testing procedure for all types of qualitative and quantitative data without requirements of large samples or specific distributional features, and can as such, for example, facilitate mixed methods research. Okay, that's it for this video, which I hope is useful. If you have any ideas or suggestions for future videos, feel free to leave a comment below this video or contact me via lappinganalytics@gmail.com. Thank you for listening and see you soon. Bye bye.